Good afternoon, everyone. We are going to be doing what I think is some really cool stuff. And we're going to be doing it, excuse me, I'm just moving some windows around, on a topic that is very relevant to today and especially tomorrow. And that is trying to estimate who's going to win an election. And the bigger picture is how you find an estimate for the population proportion P. So the population proportion P is a single number, normally written as a decimal, but very often is also converted into percentage, which represents the percentage of people in that population who said yes to whatever it is. So you could say, are you going to vote Republican? And 82% said yes, or 12% said yes, whatever it is. And have you ever been to France in your holidays? And 4% of the population would say yes to that question. So it's a very simple yes-no type situation, right? So there's a question out there, and you ask someone that question. So right now, if we forget the third parties, right, the Green Party and the Libertarian, I think it's the two major ones. To simplify the process, can we just pretend they don't exist? And so there's only two people, a Republican or a Democrat, right? And in the vast majority of those situations, that's quite realistic. Would you agree the chances that a Libertarian is going to win the presidency is zero, right? It ain't going to happen, right?
Well,
and this
pretty low, but I don't know about zero.
True, nothing is ever. Well, no. Politicians telling the truth is zero, but almost everything else is probably not zero, but very close to it, right? So that's the only simplification I'm going to do. So let's get you used to some terminology. This little fella here, with a funny little thing on it, is called p-hat. That's how you say it out loud. Now, p-hat is the sample proportion. So you go and ask people in Bremerton, maybe 1,000 people in your sample, who are you going to vote for? And the ones who said yes to Republicans, right, go there. And the total number of people you ask go there. And you calculate p-hat. So p-hat might be 0.2, which would be 20% Republican. Could be 0.8, could be 80% Republican, right? Now, that's just a single point. What we want to do, just like we did before, is isn't it much better if we can generate confidence intervals? And it's got very similar structure to what you've already seen. So I've got it over here. A 95% confidence interval is p-hat, right? Whatever the people in the sample said, right? 0.12. You do, all these calculations are done in decimals until maybe the end when you might choose to do percentages as a last resort. So p-hat, plus or minus, do you recognize this little guy? The magic z-score. He's back again. Same z-scores, same magic. And this horrible square rooty thing, this guy here, that's basically the standard deviation. That's, for a proportion, that question, that calculation is essentially the standard deviation. So let's make up a story for this 95% confidence interval. So no matter which one I pick, I'm going to annoy half of you, right? So I'm trying not to. So you ask 1,024 people, and out of that 1,024, 558 of them are going to vote Republican. So p-hat will be this ugly guy. And we turn it into a decimal. So 558 divided by 1,024 comes out at about 0.5, well, you can see it here, it's 0.5449. So how about 0.545, right? So I'm doing it to 3 decimal places. So that's 54.5% are going to vote Republican in Bremerton, allegedly. You know, if you know this number, don't you know the people who voted Democrat, the people who said, no, I'm not voting Republican? Aren't they whatever's left? So in this case, the Republicans are going to get 54.5%, and the Democrat, well, they're going to get the other 45.5%. And what that might look like is the Republicans have a 10% lead. Would you agree? 10% bigger than the other guy? Now, if you look at that superficially, if you're a Democrat, you shouldn't bother going out to vote. Your guy's not going to win, right? Still going to win. That's a very sneaky technique done by politicians to get you not to vote. They tell you polls that will dishearten you, so you won't bother turning up. And because you don't turn up, your guy doesn't win, and so the polls end up being right. You see, it's a kind of self-fulfilling prophecy. But that's just a single number. It's much more accurate if you tell us an interval, like a 95% confidence interval for what the Republican vote might look like. And that's this guy up here. So let's see what we have. A 95% confidence interval is p hat, which is 0.545 plus or minus 1.96 times the square root of 0.545 multiplied by 1 minus p hat. Isn't that basically the 0.455? All divided inside the same square root by 1024. Now, can you see that we're now back to needing calculators and not salt, where you'd like it to do it all for you, right? This is much better. So let's do the 1.96 times, do a square root. You don't need the brackets, I just put them in for emphasis. 0.545 times 0.455 divided by 1024, close the brackets, and the answer I get is 0.545, give or take 0.03 if you round it to the nearest guy 1. And I don't know why I put a bracket around that, but I did. Well, let's see what that looks like. Well, if you want to look at the lower limit, it's this guy, take away this guy, so that's 0.514. You can then get the upper limit, which in this case would be when you add them, and that's 0.576. And you get the guy called the margin of error. And the margin of error is this fella, 0.031. But most people, including me, especially with these kind of questions, isn't it easier to see what's going on when you think of it as a percentage? In this story, the Republican vote, we are 95% confident that the Republican vote is somewhere between 51, put that on a piece of paper, it's somewhere between 51.4% and could be as high as 57.6%. And this is a 95% confidence interval based on our sample, with a margin of error, which they call E, of about, give or take, 3.1%. Now, based on this pretend story, would you agree that for this pretend story, the Republican is probably going to win? Because all you need to win is 50% plus a person, right? That's all you need to win any election if it's a two-horse race. Now, we're not 100% sure. Isn't there still a 5% chance that this is just a bad sample and the Democrats going to win? Right? It's some totally different answer. Now, that was based on a sample of 1,024. Now I'm going to show you something that is why you need to be skeptical of polls. I'm going to take the same information, but with one change. It wasn't 1,024 people. The sample only we used 102 people, right? Roughly 10 times smaller. What do you think is going to happen to the margin of error if I keep everything else the same? In other words, keep these decimals the same. What's going to happen? Bigger margin of error? Smaller margin of error?
Bigger?
Yeah. Let's see how big. Now, we're assuming that we still got that guy, right? So I'm going to keep the confidence interval the same. So it's going to be 0.545, give or take, still 1.96. But now it's going to be this number times that number. I wish I'd planned it better. But the only real change, isn't the only real change one number in the entire calculation? Just that one number. Right? So everything else was the same, allegedly. So let's find out what this looks like. We've been thinking that it's bigger, which I agree it should be. 0.545 times 0.455 divided by 102. And the answer we get is 0.545, give or take 0.097. Okay. If you round it off, that's actually 0.10. Or if you like 100. Good grief. 54.5% with a margin of error of 10%. What does that look like as an interval? Well, on the low value, the Republican might only get 45.5%, and on the high value, it could be as high as 55.5%. There's a huge, huge variation on what the Republican vote is likely to be. Huge variation. In fact, based on this interval, wouldn't we use this term, which I hope you've seen before? Too close to call. You agree? Too close to call means if it's this nice big number, I guess the Republican wins. And if this nice little number doesn't end up being the other guy, the Democrat that wins. If you look at on any channel, in fact, I think I'm going to go to a channel right now and we'll show you what this data looks like and why I get annoyed at it. Because almost all of them will say, this guy's going to win, that guy's going to win, right? So Republican's going to win this state, it's going to be a Democrat's going to win this state. When you look at the numbers, there's a couple of things that are missing. Well, let's just see what they are.
Would the upper limit be 65%?
Right. God, that means the yeah, he's still going to win, but by even more, right? But you're right, I did an oopsie. So I'm going to go in and I'm going to go to a site and I'm just setting it up right now. I think this one's got lots of stuff in it. Right, here you go. So let me show you. And maybe you can see what my problem is and why I get annoyed at things. I'm going to make this as big as I can because I'm not sure how small your screen is. Right. If you look at this set of results, here is Pennsylvania. And this is them asking a number of people. We don't know the sample size, which is my first problem. Couldn't it be 10,000 people they asked? Or 100? Doesn't that make a difference? Secondly, in this case, Biden got 48, Trump got 49. Here, they're just telling you what the difference between those two numbers are. I think the reason they don't add up to 100% is that there's a Green Party and there's another, a Libertarian Party, and they always pick up 1 or 2% of the random votes that are left, right? Now, in this case here, Trump won by 1%. In this one here, Biden won by 5. In this one here, Trump won by 2. And this one, it's Biden by 7. And this one is Biden by 3. Now, that is the same state. And there are 5 different results. Not one of those buggers bothered to tell me how big the sample is and what the margin of error is. If I went through every single one of these and I told you that the margin of error was 10%, wouldn't the answer be too close to call for every single one of them? And if the margin of error was 0.1%, how come I'm getting a +7 here and then a +2 there? None of that information is any darn good to anybody who knows what to look for. When you look at that, whatever it says, whether you're a Republican or a Democrat, will you please ignore it? Because until you tell me how many people were in your sample and you tell me what the margin of error is and we do some real good math, then I'll make up my mind about whether or not that is evidence that the Republican or the Democrat's going to win. Because right now, the vast majority of these are just, I'm trying to think of a polite word. They're trying to screw with your head. They're trying to make you depressed if you're one or overexcited if you're another. And why that's a bad thing? Let's just pretend that you've looked at all the cool polls and your guy is guaranteed to win because the polls told you he was going to win by 7%. And then the other guy wins. What's going to go into your head is somebody cheated, somebody stole that election, someone fixed the vote. When the real answer is, they shouldn't have told you that data because it was so wide. They shouldn't have told you it was 7. They should have told he could be getting anywhere between 40 and 60%, pick your number. Now, if you got that data, wouldn't you be a little bit less confident about your guy winning? At least you could see there's a possibility he in both cases this time, he might not win. And that is very unscientific. And I don't know why people don't complain more about it. Maybe because they don't do a statistics class and they know how to analyze things now. So you know something they don't. And I could click on this and I could go to, I guess, that company. One of the things you got to watch, and you can almost see it, is I don't know these companies, but I'll have a guess. NBC is probably not Donald Trump's favorite TV station. Would that be a fair estimate? Now, if one of them was Fox News, that might well be, it would be one of his favorite TV stations. But unfortunately, isn't there a political bias in much of the media today? So don't be surprised when NBC makes Biden win and Fox makes Trump win. Dead easy. I want to cheat right now. I could do 5 different surveys in Pennsylvania, right? 5 different ones. But I only keep the one where my guy won, and I publish that one. And I don't tell you the other 4 because I didn't like the answer. That's how you cheat in this game. So, there, I got that out of my system. I feel so much better. You probably don't. But I hope I'm getting across to you. You've got to be skeptical of not these types of results. They are, they don't really reflect the truth unless you know the whole story. And the whole story is how many people in my sample, what's the margin of error, right? The minute you know that, you are good to go. And then you can make, oh, I've lost my picture here. Yeah, then you can make the one, yeah, I think the Republican's going to win. Or, I don't know, anybody could win, right? And that's a much better frame of mind. Let's pick some that's not political. So I'm going to use you lot. And you lot are going to vote for something, but not anything political. You lot are going to tell me something about yourself that you want to share. And I am going to count how many of you said yes. So, what kind of question should we pick? You got a question that we could ask, Bethany?
Do you have a tattoo?
Pretty good question. If you don't want to share, you'll be in the non-responders, right? And that happens. In today's political environment, there's quite a few non-responders. That's people who won't tell you who they're going to vote for. So we need tattoos. So 2, 4, 5, 10, 15, 20, 25, 35. I make it 35 people. Stick your thumb up if you want to share, you got a tattoo. You know those little thumb things that you can do? I got 1, 2, 3, 4, 5. Anybody in the next page? 6. Okay. Good question. I've lost it. Darn it. Oh, there we are. Okay. I've got so many windows up right now, it's scary. Right, you're looking at a white screen with 635s here? Good, because that's P hat. That is a very, very small sample size, 35. So do not be surprised if the margin of error is plus or minus 20% or something, right? It'll happen. Right, now, let's give us a 90% confidence interval, right? Because I decided that's the one I want. And we'll put it all together and see what we got. Right, so for a 90% confidence interval, it's going to be P hat, give or take, the magic Z score for 90, square root, P hat, 1 take away P hat over N. So what do we get? I should turn that into a percentage, shouldn't I? Or a decimal. 6 divided by 35. Oh, darn it, that's not a very nice number. I'm going to do it to 2 decimal places because I don't want to write lots of decimals, right? But if the question says 4, you got to do it to 4. Right, so this fella here is 1.645 square root of 0.17, who said they have a tattoo, and 0.83 then, who said they don't, divided by 35. On the calculator then, 1.645 times 0.17 times 0.83, all divided by 35. No, it's not. 1.645 times the square root of, there we go, 0.17 times 0.83 divided by 35. And that's much better. Well, actually, it's bigger than I thought it was going to be. It's 10% margin of error. So 17, give or take a margin of error of 10%. So somewhere in the region 17 to 27%, right? A lot of, a huge variation, but I can still say some things with a 90% confidence. I'm not 90% confident that it's less than 30%. I could even say 28, 29, 30, right? But less than 30. Would you agree that I'm 90% confident it's more than 5%? I mean, just different ways of looking at that. Now, if this, and there's a lot of ifs here, if you are a fair representation of community college students, then we could make this as a fair prediction on what all community college students would be, because that's who the population would be representing, right? If you don't think you're a fair representation of all community colleges, I think you're probably a fair representation of Olympic College, in which case that represents Olympic College students who have tattoos. Right? So you may adjust your population to what you think is a reasonable assumption to make. Now, there's a couple of assumptions that I've been making that I haven't stated yet. The first one is a kind of catch-all. I'm assuming that the sample is a simple random sample. Well, you lot aren't, because you're in my class. If I wanted a real simple random sample, wouldn't I have to go out to Olympic College and randomly pick 35 students and say, have you got tattoos? And then try to explain to security why I was asking complete strangers a question like that. Whatever. Right. But we'll assume. The next one is a little bit less obvious. NP has to be greater than 5. And NQ, oh, by the way, Q is 1 minus P. It has another name, right? Those two guys, and since we don't know what they are, we have to use a hat, have to be bigger than 5. So in English, what that means is the people who said yes have to be greater than 5, and the people who said no has to be greater than 5. And it's just it's to stop you doing a sample of 2 people and then trying to use that and project it out into the whole population. I don't think anybody would think a sample of 2 would be a good idea, but it's a kind of the bare minimum. It's also it's to cover the fact for some questions where the answer could be very rare, and it doesn't even need to be a normal question. Suppose I collected a random sample of 1,000 people and found out how many of them had pick a rare cancer, had melanoma of the face, right? Skin cancers on the face, right? Can you imagine, even in 1,000 people, that could be quite a small group. Couldn't you just get only 4 people had it? Now, if 4 people had it, you couldn't use this to predict the percentage of Americans that have melanoma on their face, right? It's just a catch-all to stop you for very rare situations. It doesn't normally happen, but in case it does, we now know, hey, sorry, we can't do it this way, hard luck. Are we comfortable with this process, how you can actually, just from a very simple sample, generate 90, 95, 99, whatever you feel like, confidence intervals? Do you feel good about this process? So time to go and look at some homework questions then? Okay, let's do that now. Okay, make this a little bit bigger. Can I make this bigger? Why can't I make this bigger? What's that? Sugar and spice. Okay, hold on a second. I want to try and make this as big as I can. I'm not quite sure how I'm going to do that. So let me close it off and open it up again and see if I can make it bigger. Okay, that took a while, but I think I've got it to work. Are you now looking at a bigger version of 7.3? Hopefully you can read it. Do you want me to make it bigger? It's fine, okay. So, a couple of baby questions just to get out of the way. For a binomial experiment, what the heck is that? We've been doing them, I just didn't call it that. What does bi mean as far as a number?
2.
So this is a question where there are two answers, yes or no. Right. All of these are in fact binomial, right? We only deal with two questions. If you ever want to do some advanced statistics, there are, what do you do when there's 3 answers? You know, or 5 answers, right? It's a totally different proposition. But we're doing bi, meaning 2 answers, yes or no. And it's R over N, right? The number that you said yes over the total number. In order to use this property, right, the confidence interval, one of these 4 dots has to be correct. Can you remember which one? We just did it before I started moving these screens around. 1, 2, 3, or 4, which dot?
2.
Both of them bigger than 5, right? That basically is how many people said yes, and that number is how many said no. But they're called NP and NQ, and that's great. We talked about these, I'll skip by them. Right, we're not going to use salt, we are going to do it the hard way. In a random sample of 67 professional actors, 35 were extroverts. That is a miraculously low number. I would have thought if you were an actor, you would just naturally be an extrovert, right? But it is what it is. So you will go here and I'll do it because you just have to trust me. 35 divided by 67. And do they mention what they want? They want 4 decimal places. So 0.5224. You just trust me on that, right? Now we're going to find a 95% confidence interval, and we'll write the upper and the lower limit there, right? So I'm going to take a little note of those numbers because we'll have to leave it in a few seconds. Can you kind of judge what's going to happen? You know, what I'm going to be doing in a few minutes, right? I got a sample size here. I better put that in as 67, and I'm being asked to find a 95% confidence interval. Okay, so we'll leave this question for a few moments. And this is kind of what you would be doing anyway, right? You'd have a piece of paper and you do your working, right? I need 3 monitors. That's what I need. Do any of you want to chip together and send me another $500 so I can get a cheap monitor? Holly, you're rich. You travel all over America. You got plenty of money. Okay. 95% confidence interval. P hat plus that guy square root this guy over N. So let's see what it is. 0.5224. That's him. plus or minus a 95er is 1.96 again. Square root of this guy, 0.5224. The guy called 1 minus p hat all over 67. Anybody want to volunteer what the second decimal is going to be? If you know this one, you kind of should know that one, right?
0.4776.
You all agree? Okay, and then it's calculator time. 0.5224. No, it's not. I do this first. 1.96 times square root of 0.5224 times 0.4776 divided by 67. And we are looking at 0.522 plus or minus 0. What am I doing that for? 224. That says 224. Plus or minus 0.1196, because everything has to be 4 decimal places, which is a real pain. Lower limit, upper limit. Right, that guy, add that guy gets me the upper limit. So I'm going to add 5.224 and I get 0.5224, that's better. Add 0.1196 and I got 0.642, which is what, about 64.2%. And then 0.5224, take away that guy. 0.5224, take away 0.1196. And we're looking at 0.4028. So somewhere in the region, what, 40 to 64% of actors are extroverts, based on a sample of 67. Okay. Based on this interval here, right, from there to there, I'm 95% confident that it's more than 40%. Would you agree? More than 40% of actors are extrovert. If I look at this number, what, less than 65%? Big range. So I'll now return back to what it looks like as far as we're concerned for the homework. And the lower limit question. Very good. Okay. Lower limit is 0.4028 and the upper is 0.642. And then I'm 95% confidence. It says in the next bit, do you think that this condition is satisfied? Well, if you look at who we've got, would you agree that more than 5 people are extroverts? Would you also agree more than 5 people are not extroverts? Because that would be what, the other 32. So yes, 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 and off you go. Now, once you've got that gist of this process, you know really all they do is change the story. Right? It's Republican and Democrat was the one I did. This is extroverts and introverts, I guess. The next one is a sample of 5,000, and they found out that this number of them were in a particular traditional style. So can you imagine what your p hat's going to be? It's going to be this big number divided by this huge number, right? I can make a prediction. Do you know the margin of error on that is going to be quite tiny? And the margin of error really depends for the most part on this number. That number, as long as it's not extremely small or big, doesn't make that much difference. It's kind of give or take a couple of percent at most. This is the guy that makes the difference. If I made that 50,000, you know, I could shrink the margin of error to less than 1%. So you would know it's 59%, give or take 0.1%. You know, that's how accurate you can make it. So the moral of the story is very simple. Get a big random sample. The biggest you can afford to pay for if you want a really accurate data. Now, if you want to lie to people, ask 50. Actually, ask 50 people 7 or 8 times, right? Different people. And only pick the one that gave the answer, right? Have you ever heard the phrase, keep asking the question till you get the answer you want to hear? That's what they're doing in that case. So, do you get the feeling I am skeptical about political polls? Have I convinced you that you should be? Right? If they tell me the sample size, you've made a friend. I can do the rest. And I'll decide then whether that is evidence. And they go in and they ask you some NPQ questions. Here's one that should scare you. Of the 10,500 and yeah.
Oops, sorry. For number 6, I had a question because.
Oh, yes, go for it.
I understand how to get p hat, but for the q hat, how would we solve for that?
Oh, dead easy. I'm making this number up just to show you how you do it. If this was 0.1234, q hat is the rest, 0.8766. Just take p hat away from 1.
Oh, okay.
That's all you need. I call it 1 minus p hat in my formula. In other textbooks, they use q hat instead of 1 minus p hat. I think it's easier if I just have one thing called p hat everywhere rather than a p and a q. But yeah, a good question. Can you imagine we did the prisoner one? It might scare you how many guys actually escaped if that was true data. This is about trout. Is this data real? Don't know. Now, normally, if it's true data, they have a little plus thing you can click on. You can find out where they got it. But here is one about how many fish that died. I kind of think that's true, although I've never fished in my life. But, you know, when they catch the fish and they bring it out and they take the hook off and they chuck it back in the water, yeah, I kind of think a lot of those fish don't make it. I mean, they're probably in danger of being eaten by something else because they're really tired and kind of hurt, or infections or whatever. That was that story.
I have a question.
Yes.
What does salt do?
If you click on salt, I don't want us to use it, especially for the test as well. I guess I could click on it and see what it does. It does that. And if we click on sampling, regression, inference, oh, good. It's totally useless for these questions. So I'm kind of happy. I didn't want us to use it. And you couldn't use it anyway. It doesn't use the numbers, at least not in the one I clicked. Salt's really useful for some of the other, you remember some of your homework, which was dead easy because salt did all the mean and standard deviation and helps you find the t-score and all that stuff. But in this case, where are we doing this? I've lost it. I closed too many windows. Right, put this back in. There we go. So in this case, it doesn't do anything useful, so I wouldn't worry about it. But it is useful in other questions, other homework questions, and not these. I'm trying to see if I can get to one last guy, because there's another thing we need to do on these. Do you want me to do one more of these, or are you kind of happy we know the process?
You do one more.
Okay. I'm on 9, might as well use it. It's as good as any other, right? So in question 9, everything's to 4 decimal places. Answers might vary a little bit because of rounding off, okay. In a market survey, a sample of 984. So I'm writing down on my paper, N equals 984. That's the sample size. 266 always stock up on an item when they find that item is a real bargain. So if beans and sausages are at half price, they buy a dozen cans of beans and sausages. If you're anything like my poor mother, she would do that, and nobody liked beans and sausages. She just liked the idea it was half price. But I wonder. P hat then is 266 people would say, yes, I'm the kind of person who would do that. I would buy, you know, a dozen cans if it was half price, even if it wasn't stuff I liked. I'm not asking anybody here to share that piece of information, but you may be one of those. So let's put that together and build through the question. They kind of tell you what they want you to do in, you know, do this first, do this second. So the first answer is A. They want you to find the estimate, right? Basically, they want you to find that guy. Well, don't you just divide the yes votes with 984? So 984, no, clear that. 266 out of 984. Into 4 decimal places, 2703. I should have actually written it there. And then they want you to do in part B. Oh, come on. I'm getting tired. That's 95%. That's the third 95%. Do you know you can be asked 90s and 99s as well, right? It just hasn't happened. But anyway, back to the question. They want yet another 95% confidence interval. I'm writing the formula down because I think if you write it down enough times, it'll just stick in your head. So far, so good? Right, so let's put all the numbers together and see what we get. We get a p hat, 0.2703, give or take a magic 95, which is 1.96, times p hat, 0.2703, times q hat, or as I call it, 1 minus p, of 7297, all divided by 984. Let's see what that looks like.
Where'd you get the 7297 number?
I subtracted this number from 1.
Thank you.
So I go here and I'll type this in. 1.96 times square root 0.2703 times 0.7297 divided by 984, and I am looking at 0.0277. And the upper and lower is what they're asking you for. And I've probably put in the wrong order, but that's fine. If you add these two together, you get the upper, so let's try that. 0.2703, add the margin of error, and it ends up being 0.298, and then 0.277 0.703, take away 0.0277, and I hope I did this right, it's 0.2426. And because I'm a human being, somewhere between 24.6% all the way up to 29.8%. And so that is the percentage of people who said they would, in the whole population, that's somewhere in that range is the percentage of people who would buy a dozen cans if they were half price. Okay, does this experiment, does the NP greater than 5, NQ greater than 5 work? Yeah, by a whole chunk, right? And so it's good to do this process. It works nice. Now, this is their question C. As a news reporter, how would you report the survey result on percentage of supermarket shoppers who stock up? So you imagine they're doing a morning show and they'd say, hey, Gallup polls just got a new poll about how people shop when there's sales on. Do you think they're going to say the upper limit is this decimal and the lower limit's that decimal? Not in a TV show, right? People would just look and say, what? Right? They could do it two ways. They're most likely to go for the simplest one. Wouldn't they just say 27%? That number? 27% of people shop for bargains by buying a dozen cans of beans when they're half price. Now, if they've been a bit more accurate, shouldn't they say 27%, give or take 2.8%, or at least tell me the margin of error? I don't think they do very often because too much information confuses people who don't know what it's telling you. But to me, that tells me more than that. Are we good? So I'm going to do one pet peeve to get it out of my system, and it's connected to this. So here we go. What percentage of people in the United States of America have had or still have COVID-19? Now, we're not going to actually collect that data. We're just going to look at the problems of collecting that data. I would like to know, have 20% of Americans already caught COVID, got over it, got better, and now are fine? You know, like you caught the flu. Or they've got it right now and, you know, maybe they're fine, maybe they're not.
20%.
Right, but let's figure out how you can collect that number. How would you, say again, Christian?
You would collect it through testing, like positive results, right?
Well, is that the right answer? Well, you could say we've tested a big chunk of the population and we found out that of all the people we tested, making this up, 35% had COVID. Well, 35% of those we tested had COVID, right? Making that number up. It could be 5%, right? But whatever it is, right? And you're saying that if you look at the people you've tested, whatever that number is, that's a reflection of the entire population. I could argue that that's not a good number. Who gets tested for COVID?
People with symptoms.
Right. So won't that be higher than the real number?
Yes.
But we don't know how much higher, do we? As far as I know, and it's amazing to me that no one's done this, do you know the best way to find out what that number should be? Shouldn't you collect a random sample a simple random sample of 1,000 American adults, let's say we focus on adults, and test them, whether they were sick or not, whether they felt bad or not, wouldn't that be a true reflection on the percentage of Americans who get COVID?
It'd be a better reflection.
It would be a better reflection, a more accurate reflection. But that's not the one that we get. Aren't we typically getting, I don't know what the number is on now, 500,000 Americans have tested, no, it's more than that, isn't it? Like 2 million Americans have now tested for COVID. Whatever that number is, right? But that's basically the tested ones. So if you want p-hat, shouldn't you test 1,000 people and get, I don't know what the number is, right? Whatever the number is, and that's you got that one. As far as I know, no one's done that yet, which is really strange. I don't know why. I mean, governments have tons of money, right?
So I want to ask a question about this. And the question is basically like how good, I guess this logic works. So what I was just assuming what they're doing is like, oh, well, we'll just assume everybody that doesn't have symptoms doesn't have it, which of course isn't true. You could still have it and just have no symptoms. But
yeah, asymptomatic.
How good is it if they have all of the positive cases over the total population of the United States and calculate the percentage that way?
That would be an underestimate of the truth. If what you said is the people who have got symptoms divided by the total number, that would be an underestimate, because there's lots of people who are asymptomatic. There are lots of people who have had COVID. In fact, there might even be one of you here and didn't even know it, right? You had a couple of days where you think you were coming down with something and then you didn't. You know, the kind of, I think I might be catching the flu, but I didn't kind of thing. You might have been a COVID, you might not. You might have been just, you know, having a bad day. We don't know who those people are because we don't test that way. That makes that figure quite difficult to get. Well, I wasn't going to do this one, but give you a different problem. What percentage of people die when they catch COVID? Right, it's called the fatality rate. That's a very important number. See if the fatality rate is like 90%, which I think is what it was for, oh God, that one in Africa. You know, the one that made you bleed and you died? Ebola, right? That's some ridiculous, like a 90+% death rate, right? If you caught it, you were in real trouble, right? You know, pretty much every disease has a death rate. Do you know that the flu has a death rate? You know, before this happened, you know, every year, not a huge number, but a noticeable number of people would die from complications from the flu. Now, they tended to be, and this won't surprise you, people with underlying conditions and illnesses, right? Bad heart, obese, breathing issues, right? So what percentage die of COVID? Well, you know, the only way you need to know that is, don't you need to know what the bottom number is? Which basically is back to my original story. We don't know the bottom number, really. The only way we could do that, I guess, would be to do a sample of 1,000 or to test everybody. Do we know the top number then? How many people die of COVID? Well, you don't need to know the number, but can you imagine how they would know? Right, you're in hospital, you've tested for it, and you drop dead. God, that's cruel, isn't it? But you died, right? That's a definite dying of COVID, isn't there? Do some old folk die at home? They had COVID, but they die. They never got to hospital, right? They get a death certificate. If they don't test the person, couldn't they just say, well, he was 90 years old and, you know, for want of a better word, he died of old age, right? I mean, everybody dies of something, right? So that's hard to tell. There are some countries in the world that count COVID deaths in different ways. So you can't even compare one country with another. Do you know, if you are in a car accident and you happen to be asymptomatic, but you had COVID and you're in a serious car accident, they take you to hospital and they test you for the protection of the nurses as well as you, right? You'll test for it. But you know you died of the car accident, right? In some countries, you are considered a COVID death because you had COVID and you died. And in other countries, you are not considered a COVID death because the COVID wasn't the major reason you were killed. You died, right? Now it gets into a really grey area. If you're really weak, bad lungs, old, congestive heart failure, right? You can catch COVID and you will die. Did the COVID kill you, or was it your congestive heart failure that killed you? So you can see that top number is fraught with danger. The bottom line is, I don't know what percentage of Americans die of COVID. I don't know what percentage of Americans have had COVID. And I don't think anyone else does either. And so we have to look at that and say, well, that's not very good, right? I want to know those numbers because that tells me a lot about how dangerous this bloody disease is. Right, we are about to start our next section. I know that you're looking forward to that because I got to rant on, and I hope I didn't offend anybody because I kind of spend a lot of my time doing that, it seems lately. Must be getting old. Right, just taking a few seconds because I had to look up some notation, which is a real pain in the butt. But here it goes. We're going to look at how do you estimate the difference in two proportions. Right. I'm just basically writing a formula down right now. Okay, we got it. And let's see where we're going. Oh, have you been seeing this as I've been writing it? Okay. Right. So I probably should write it a bit neater for you. Right. So we're going to look at, for the second part of 7.3. How to estimate the difference in two proportions. So let's do a story. Let's do United States of America against Scotland. And we are going to look at what percentage of Americans and what percentage of Scottish people drink too much. So in America, they got a sample of 1,000 people, so we'll call it N1. And of that 1,000 people, 320 of them said they drank too much. or were tested and found out that, you know, you say to them, how many do you drink in a week, right? Whatever way you get it, but that's the number you came at. And we go to the Scots, and there's only 400 of them that we asked. And the percentage of these ones was 200. Now I'm going to turn both of these things into a percentage just so that we can compare the raw data. So this one here is 32% of Americans drank too much, and over here it's 50% of Scottish, to be stereotypical, right? So the question becomes, is there a distinct difference between these two? And how much is that difference? Well, if you look at the two numbers, isn't it easy to tell 18% more Scotsmen than Americans, right? That's the difference. But we want to create a confidence interval for that difference. And that's the trick, the confidence interval part. Which means that somehow we have to marry together the fact that these two samples are different sizes and that these two answers were different as well, right? Which is not a surprise. And so this is what this formula over here is. Let's do a 90% confidence interval on the difference. So P1 hat take away P2 hat, plus or minus the magic Z score for 90%. So far, so good. And then, darn it, would you look at that ugly formula? Can you remember what Q hat was? Because I called it something else. I called it 1 minus P hat, didn't I? Since this formula is so big and ugly, can I start calling Q's in these guys, right? So Q hat just means 1 take away P hat. It just is going to make writing down formulas a little bit smoother. So it's going to be P hat, which is 0.32, take away 0.5. Oh, by the way, we work with decimals in all calculations. Give or take, we're still using this guy, 1.645. P1 hat, 0.32. What number is Q1 hat? This is P hat. What decimal is Q hat?
0.68.
Right. Are you getting used to taking the other guy away from 1? Right, so if one of them's 0.3, the other's 0.7. If one of them's 0.2, the other's 0.8. This one's a little bit weird, but it is cool. 0.5, 0.5, right, because 0.5 yes, 0.5 no, and 400. Now this is going to be a really messy calculation. And I don't know why I didn't subtract them, but too late now. .645 times a really weird square root. This guy plus this guy. So 0.32 times 0.68 divided by 1,000. Then you can go add 0.5 times 0.5 divided by 400. And then you can hit enter. And you will get, in this case, 0.05 because I'm rounding it off. Now this guy away from that guy is a negative number, which is okay. Give or take 0.05. So that makes the lower limit, that take away that is even more negative. And an upper limit, that take away that is still negative, but not quite as bad. So negative 23% to negative 13%. And that is the difference, right? Between Scottish and Americans. The difference is somewhere between negative 23% and negative 13%. Okay, let's try and make this a little bit more easy to figure out what it's saying. The fact that this is negative, doesn't that mean Americans drink, overdrink less than Scottish? We agree? If this was positive, wouldn't it mean Americans are bigger? So if the interval is negative, it just means the first thing is smaller than the second thing. That makes sense? Now, when I look at this percentage, couldn't you say that it's somewhere in the range of 23 to 13? Right, so they drink less 23% of the time, or maybe 13% of the time. But that is to me very significant evidence that Americans don't drink anywhere near as much as Scottish people. If I swapped places, wouldn't the only thing that changes that these would become positive numbers? And of course, 13% goes first and 23% goes next. Actually, when it's that way around, isn't it easier to tell? Scots guys drink 13% more, up to as much as 23% more than an American would. So why are differences like this important? Well, one of the ways that they get used, this will be my last question today, would be in comparing old treatment to new treatment, right? So let's suppose that we have a new hip replacement surgery technique, right? They figured out a different way of doing it compared to the old way. So there's the old way, right? Let's rephrase it. Let's do the new way. And we want to compare it to the old way. And they looked at 100 people who were given the new operation. And we compared that against 500 people who were given the old operation. This could quite easily be a clinical trial, you know? Maybe it's, I don't know, do they use titanium still, or is it ceramic? What do they use in hip replacements now? Anybody know?
I think it's a combination of both.
Okay, so it used to be just titanium, but that didn't work so well, so they did ceramic, but maybe ceramic wore out too quick, so when you do a bit of both, they got the thing, right? Okay, that'll work. And you then have a measure of success. Sometimes you have to kind of fudge this one, but maybe a measure of success is the number of people who took that operation and were now mobile, right? They didn't end up in a wheelchair. Maybe it's something as primitive as that. And in this one, 65 out of 100, no complications. After the operation, 6 weeks later, they're running around like a young'un. And then that's called N1, of course. And N2, let's suppose that it was only 255 out of 500. Now, if I put these as percentages, only so we can get a feel for what it is. This new operation has a 65% success rate, and this operation, the old operation, just doing this on my calculator, They had a 51% success rate. So I'm trying to, a successful. I wanted these to be significantly different so that we could get at the end a conclusion that we could justify. The conclusion I want to get is I want to prove that the new operation is more successful than the old one. And therefore, people who do hip replacements should now be doing this new way to do it and use whatever it is that you're using, right? The new ceramic titanium combination thing. Well, we got everything we need. We just need now a confidence interval. Why do you think I'm picking a 99% one rather than one of the other smaller numbers? And that's pretty typical in these kinds of stories, that you always go for a 99. Why do you think I want to be so sure that when I say something, it's true that it's true? That's really the argument.
Because it can severely affect someone's life.
Yeah, you don't want to say, yeah, this new operation is really good because you used an 80% confidence interval. Because if you used an 80% confidence interval, couldn't you just end up being one of the 20 that was wrong and you were hurting people rather than helping them? Because the alternative to this is that whatever conclusion I make may be wrong, but at least it's only going to be wrong 1 in 100%, right? 1 in 100 times. And you can't have perfect, so you got to live with what you can do. So 99 it is. So it's going to be P1 hat, take away 2, right? And 99 is 2.58. It's going to be P1 hat, Q1 hat over N1. It's going to be a P2 hat, Q2 hat over N2. You're happy about this ugly formula? Let's see what we get. P1 hat is 0.65. P2 hat is 0.51. Give or take 2.58. Okay, this guy is a 65-35 split divided by 100. And this guy here is a 51-49 split divided by 500. Take that away from that and you get 0.14. So it looks like there's a 14% improvement, right? But let's see what the margin of error says. It could just be luck, right? So the margin of error puts a band on, how this could happen. So I'm looking at 2.58 times the square root of a 65-35 split divided by 100 added to a 51-49 split divided by 500. And the answer I get is plus or minus 0. I wasn't expecting this, 136. 14% give or take 13.6%. So somewhere between a 0.4% improvement, but it could be as high as 27.6% improvement. Double check my percentage here. Yep. So would you suggest, if it was your grandmother, that she should do the new guy or stick to the old guy? Well, they're all positive, right? So she's going to get some benefit. Now she may get hardly any, right? But it's, one more person out of 250 get a better result. But it could be, more than 25% benefit, right? A lot of benefit, right? What would be the only way I could reasonably alter this story to try and improve on the accuracy? So I want to see if I can separate the difference between them more by doing something. There's only really one thing you can do that's not cheating.
Increase the sample size, maybe?
Yep. Very often when something new is happening, like maybe the only difference here is the joint, right? The new hip, right? Maybe that's titanium, or maybe this is ceramic and titanium, right? They very often do a baby trial, right? A small trial. And that tells them whether it's worthwhile forking out a lot of money to do a major trial, right? So a major trial would have thousands of people in your control group, right? And your experimental group. And if you have samples of 1,000, this calculation will shrink your margin of error. And so that will tell you in a much more accurate way what the benefits are. Right. See if the benefits, I'm just making this up, but can you imagine the benefits came out to be 0.9% to 1.1%? Okay, it's like a 1% improvement, right? 1 in 100 people get a better result out of it. Suppose this operation and the stuff they use is 10 times more expensive than that one. Which one do you get? What's your insurance company going to pay for? Right? Now, if you're a film star, you'll get this one, right? It's only a 1% better, but it's, you know, you always get the best, don't you? If you've got the money, you pay for it. Do you know what they do in Britain? You'll never get that. Because they do a numbers game. We can give 10 old people a hip replacement for one of these. Do the math. That's why you'll not get open heart surgery when you're 90. Cost a lot of money. And they could give it to an 18-year-old. So does a 90-year-old get it, or does the 18-year-old get it? So be careful what you don't pay for. Got my little dig in there as well. Okay, we had a nice day today. We learned some cool stuff.